NASA's James Webb Space Telescope, JWST, has once again demonstrated its groundbreaking capabilities, this time by discovering a gravitationally lensed supernova, providing an exciting new piece to the puzzle of the Hubble tension. The Hubble tension refers to the ongoing discrepancy between measurements of the current rate of expansion of the universe, known as the Hubble constant, when determined through different methods. This discovery has the potential to offer significant insights into one of the most perplexing issues in modern cosmology. The universe has been expanding ever since the Big Bang, and understanding the rate of this expansion is critical to unraveling the story of cosmic evolution. The Hubble constant, h, which describes the rate at which galaxies are receding from each other, is a key figure in cosmology. However, there are two main ways to measure h, and unfortunately they don't agree. One method involves observing the early universe through measurements of the cosmic microwave background, CMB, radiation, while the other is based on observing supernovae in relatively nearby galaxies. The tension between these two results, hence the term Hubble tension, has left scientists grappling for answers. The discovery of a gravitationally lensed supernova by the Webb Telescope adds an entirely new tool to the astronomer's arsenal in resolving this tension. But before we dive into the significance of this discovery, let's first understand what gravitational lensing and supernovae are, and why they matter in this context. Gravitational lensing occurs when a massive object, like a galaxy cluster, warps the space around it so significantly that it bends the light of objects behind it. This bending of light can amplify the brightness of distant objects, acting as a cosmic magnifying glass. In the case of JWST's latest discovery, the gravitational lens is enhancing the light of a supernova, which is the explosion of a star at the end of its life. Supernovae are crucial for measuring distances in the universe because they have a consistent intrinsic brightness, which makes them reliable, standard candles for determining distances. When gravitational lensing occurs with a supernova, it doesn't just amplify the light but can also split the image of the supernova, creating multiple images at different times due to the different pathways the light takes around the massive object. This time delay between the images allows scientists to gain unique insights into both the expansion of the universe and the nature of dark matter. This is where NASA's Webb discovery becomes so exciting. Gravitationally lensed supernovae offer an independent method to measure the Hubble constant. Unlike other measurements, which either look at the universe's earliest moments or more local galaxies, gravitational lensing sits somewhere in the middle. By studying the time delays between the multiple images of the lensed supernova, astronomers can determine the universe's expansion rate at a crucial intermediate distance. NASA's James Webb Space Telescope was designed to observe the universe with unprecedented clarity, and it has already exceeded expectations since its launch. Equipped with its powerful infrared instruments, Webb is particularly well-suited to study phenomena like gravitational lensing. It can peer deeper into the universe than the Hubble Space Telescope, capturing light from objects formed shortly after the Big Bang. The gravitationally lensed supernova discovered by Webb represents a breakthrough in the study of cosmic expansion. Not only has the supernova been lensed by a foreground galaxy cluster, amplifying its brightness, but the Webb telescope sensitivity has enabled astronomers to resolve multiple images of the supernova, allowing them to make precise time delay measurements. These time delays offer new data points in the effort to resolve the Hubble tension, providing a method of measuring cosmic expansion that sits between the early universe, CMB measurements, and local universe, supernova observations methods. By analyzing this lensed supernova, scientists can effectively use the universe itself as a laboratory to test different expansion rates at different times in cosmic history. This is a key step toward resolving the Hubble tension. To fully appreciate the significance of this discovery, it's important to understand the Hubble tension in greater detail. The tension arises from two distinct methods of measuring the expansion of the universe, each giving a slightly different value for the Hubble constant. The first method relies on the CMB, which is the faint glow left over from the Big Bang. The European Space Agency's Planck satellite, launched in 2009, measured the CMB with great precision. From these measurements, astronomers can estimate the rate of expansion in the early universe and extrapolate to today's expansion rate. This approach yields a Hubble constant of about 67.4 kilometers per second per megaparsec, km/s/mpc. The second method involves observing supernovae in the local universe. These type Ia supernovae are considered standard candles because their intrinsic brightness is well known. By measuring how dim they appear from Earth, astronomers can calculate their distance and, in turn, the rate of expansion of the universe. This method gives a different result for the Hubble constant, around 73 kilometers per second per MPC. The difference between these two measurements, roughly 6 kilometers per second per MPC, might seem small, but it is statistically significant. This discrepancy, dubbed the Hubble tension, suggests that either there is something missing in our understanding of cosmology or that new physics beyond the current model of the universe may be required. The discovery of the gravitationally lensed supernova by the Webb Telescope provides an independent way to measure the Hubble constant. The time delays between the multiple images of the supernova give astronomers a new method to measure the universe's expansion at an intermediate distance, bridging the gap between the CMB measurements from the early universe and the supernova measurements from the local universe. By studying the lensed supernova, scientists can better understand the large-scale structure of the universe and the distribution of dark matter in galaxy clusters. These factors can influence the paths that light takes around massive objects, and by measuring the time delays, scientists can fine-tune their models of cosmic expansion. If the Hubble constant derived from this method agrees with one of the two previous methods, it could help break the stalemate and offer a solution to the Hubble tension. Alternatively, if the lensed supernova provides a completely different value for the Hubble constant, it might indicate that there is something fundamentally new and unknown about the universe that we have yet to discover. NASA's Webb Telescope continues to push the boundaries of what we know about the universe. The discovery of this gravitationally lensed supernova is not only a testament to Webb's powerful instruments but also a critical moment in the quest to resolve the Hubble tension. In the coming years, more observations of lensed supernovae and other distant objects will be essential for refining measurements of the Hubble constant. Furthermore, other upcoming observatories, such as the Vera C. Rubin Observatory, will complement Webb's findings by mapping large-scale cosmic structures and providing even more data to solve this cosmic puzzle. Scientists are also looking at other potential explanations for the Hubble tension, such as the influence of dark energy, changes in fundamental constants over time, or the existence of new particles. The discovery of the Webb-lensed supernova opens the door to new methods of investigation, helping astronomers close in on the true rate of cosmic expansion. NASA's Webb discovery of a gravitationally lensed supernova marks a significant breakthrough in our understanding of the universe's expansion. It brings us one step closer to solving the Hubble tension, potentially transforming our view of cosmology. With more discoveries like this on the horizon, the next few years promise to be an exciting time for anyone interested in the mysteries of the cosmos.